Welcome to part 4 on propositional logic. Recall the two tautologies called De Morgan's laws, which say that the negation of x or y is equivalent to the negation of x and the negation of y. The negation of x and y is equivalent to the negation of x or the negation of y. You can see the first tautology depicted here via parse trees. The parse tree of the left-hand side appears here. The parse tree of the right-hand side appears over here. Okay. Let us define a notion called De Morgan dual. So given a Boolean formula phi that is over three types of logical connectives. These are the logical connectives or, and, not, or, and, not. Consider the following replacements that one could apply. Whenever one sees a variable xi, replace it with not of xi. Whenever one sees not of xi, replace it with xi. If you see an or, replace it with an and. If you see an and, replace it with an or. What do you get? So let's consider the following example. I have a formula phi, and it reads x1 or not x2 and not x2 or x3. Now let's apply these replacements. So we see x1 in yellow, we replace it by not x1 in yellow. We see the or, we replace it with an and. We see the not x2, we replace it with x2. We see the and, we replace it with an or. Not x2, replace it with an x2, or replace it with an and. x3, replace it with a not x3. This is called the dual of phi. Now, you may ask, what is the semantic relation between phi and the dual of phi? Okay? So, strange question. Instead of defining the De Morgan dual as I did here, let's define it using a recursive algorithm. This will make our life easier when we want to employ proofs by induction. So here's a definition of the De Morgan dual of a Boolean formula phi over the variables x1 up to xn and the logical connectives not, or, and. Okay, three logical connectives. And this is basically the same thing that we just showed, but described in a recursive fashion. The base cases, well, in the base cases, the formula either is a constant, a variable, a negation of a constant, or a negation of a variable. These are the four base cases. In these cases, if phi is a constant, we return the other constant. If it's a 1, we return a 0. If it's a 0, we return a 1. If it's a negation of a 0, we return 0. If it's a negation of a 1, we return 1. If it's xi, we return not xi. If it's not xi, we return xi. So these are the base cases. The reduction rules. When the formula has a parse tree that consists of more than two nodes, then we apply the reduction rules. The reduction rule, when phi is the negation of phi 1, we apply the De Morgan dual recursively on phi 1 and add a negation at the end. If phi is phi 1 and phi 2, we compute the De Morgan dual of phi 1, De Morgan dual of phi 2, and put an or between them. So an and became an or. And here, if phi is the or of phi 1 and phi 2, we replace the or by an and apply the De Morgan dual recursively to the subformulas phi 1 and phi 2. Let's see two examples of the execution of the De Morgan dual. In the first example, my formula is x and not x2. So I have the rule that the De Morgan dual of phi 1 and phi 2 is the De Morgan dual of phi 1 or the De Morgan dual of phi 2. So this is my phi 1. I apply the De Morgan dual to it. I replace the and with an or, and I apply the De Morgan dual recursively to not of y. The De Morgan dual of x is not x. The De Morgan dual of not y is y. So the De Morgan dual of x and not y is not x or y. Let's see another example. What is the De Morgan dual of not of x or y? Well, I have a not here, so I apply the rule. De Morgan dual of not of phi is the negation of the De Morgan dual of phi. So the not goes outside, and the De Morgan dual goes inside. Now I apply the De Morgan dual to x or y. I have the rule that the De Morgan dual of phi 1 or phi 2 is the De Morgan dual of phi 1 and the De Morgan dual of phi 2. So now I take the De Morgan dual of x, De Morgan dual of y, and I replace the or by an and. Good. Now the De Morgan dual of x is not x, the De Morgan dual of y is not y, and I get this formula. Okay, so by now I hope that you have understood what the De Morgan dual of a formula is. Now we want to prove some properties. The first property that we want to prove is that if phi is a Boolean formula, then so is the De Morgan dual of phi. I'll leave this as an exercise. This is an important exercise. Don't skip it. Now I want to prove the following theorem, that for every Boolean formula phi, the De Morgan dual of phi not only is a Boolean formula, but it is logically equivalent to the negation of phi. Okay? So this is the theorem I want to prove now. And we will apply this theorem to obtain the following corollary. So, assuming the theorem is correct, what the corollary stipulates is that for every Boolean formula phi, if you apply the De Morgan dual twice, you get a Boolean formula that is logically equivalent to the formula you started with. And you may ask, why is this of any interest? But let's first understand why the corollary is correct. Well, you remember the tautology that x is logically equivalent to twice the negation of x. Okay, so by the theorem, the De Morgan dual of phi is logically equivalent to the negation of phi. The De Morgan dual of the De Morgan dual of phi is logically equivalent to the negation of the De Morgan dual of phi. So now what I do is I can substitute the De Morgan dual of phi with the negation of phi. I can substitute the De Morgan dual of the De Morgan dual of phi with the negation of the De Morgan dual of the negation of the De Morgan dual of phi. So I get twice the De Morgan dual of phi, and now phi is logically equivalent to the negation of phi. This is by the principle of substitution in a tautology, which we have seen in the previous parts. So that explains why this is indeed a corollary of this theorem. So now we're left with the proof of the theorem. Okay, so we want to prove that the De Morgan dual of phi is logically equivalent to the negation of phi. The proof is by complete induction on the size of the parse tree of the formula phi. Let us denote the size of the parse tree. This is the number of nodes in the parse tree of phi by n. The induction basis for n equals 1 or 2 is proved as follows. Well, if n equals 1 or 2, then phi can be only one of these formulas. It could be 0, it could be 1, it could be xi, it could be not xi, and I forgot two cases, let me add them. It could also be not of phi, not of 0, or not of 1. Now I'll leave it for you as an exercise to check that in all of these 6 cases, it is indeed true that the De Morgan dual of phi is logically equivalent to the negation of phi. Okay, so you need to check this. Okay, the induction hypothesis says that if the size of the parse tree of phi is less than or equal to n, then the De Morgan dual of phi is logically equivalent to the negation of phi. Now we want to prove the induction step for a formula whose size is bigger than n. Okay, if the formula has a large parse tree, the root is labeled either by a negation or by an and. So phi is one of 3 types of formulas. It's either a negation of a subformula phi 1, the or of 2 subformulas phi 1 and phi 2, or the and of 2 subformulas phi 1 and phi 2. There's a missing one here. Let me add it. Good. Let's prove the second case, where phi is the OR of phi 1 and phi 2. This should be a 2. Okay? Good. Let's apply the De Morgan dual to phi. The procedure puts, instead of the OR between the two subformulas, it puts an and it applies the procedure recursively to phi 1 and phi 2. Okay. Now, by the induction hypothesis, the De Morgan dual of phi 1 is logically equivalent to the negation of phi 1. The De Morgan dual of phi 2 is logically equivalent to the negation of phi 2. So we can replace this fellow by this fellow, and this fellow by that fellow. How can we do that? By applying the induction hypothesis and the principle of substitution. Because if this subformula is logically equivalent to this one, and this subformula is logically equivalent to that one, then we can do the replacement and we get a formula which is logically equivalent to the original formula. Good. Now, we want to do the transition from here to here. What is this transition? This transition is just applying the De Morgan tautology to the negation of x, and the negation of y is logically equivalent to the negation of x or y. So we have a De Morgan tautology, and we apply substitution. We substitute. Instead of x, we write phi 1. Instead of y, we write phi 2, and we get the last transition. And indeed, this last equation that we got is exactly the negation of phi. So we got that the De Morgan dual of phi is logically equivalent to the negation of phi, which is what we wanted to prove. Good. So we're left with two more cases. Phi is the AND of two subformulas, or phi is the negation of a subformula. I leave the case in which phi is the AND of two subformulas as an exercise. Make sure that you know how to prove this case. And now I will prove the case that phi is the negation of phi 1. Okay. The De Morgan dual of phi, by the definition of this procedure, is the negation of the De Morgan dual of phi 1. Now we can apply the induction hypothesis on phi 1. Replace phi 1, the De Morgan dual, of phi 1, by the negation of phi 1. Okay, so here again I applied the induction hypothesis on phi 1, and I applied substitution, because the De Morgan dual of phi 1 is logically equivalent to the negation of phi 1 by the induction hypothesis. So I get now the Boolean formula negation of the negation of phi 1. Okay, now negation of phi 1 is exactly phi. So I write here, this equals the negation of phi. And I got that the De Morgan dual of phi is logically equivalent to the negation of phi as required. This completes the proof of the theorem, and I have already argued why the corollary follows from the theorem, so we can move on. Let me define a special form of formulas called negation normal form. We say that a formula is in negation normal form if negation is applied only directly to variables or constants. I want to remark that the negation of 0 is 1 and the negation of 1 is 0, so we can easily eliminate negations over constants, but let's not worry about the case in which you have negation of 0 or negation of 1. So, formally speaking, a Boolean formula phi, using the connectives or, and, not, is in negation normal form if the parse tree of phi satisfies the following condition. If a vertex G is labeled by negation, then if a vertex V in G is labeled by negation, then V is a parent of a leaf. So I should have here the letter V. If a vertex V in G is labeled by negation, then V is a parent of a leaf. Let's see two examples. This is one example, not of the OR of XY. The second example is AND of the not of X, not of Y. So we know that these two Boolean formulas are logically equivalent by the De Morgan tautology. But look, here the not is applied to an OR. Therefore, this formula is not in NNF, not in negation normal form. Whereas here, the negation is applied to a variable, a leaf, and here it is again applied to a leaf. So this is in NNF. Okay? So in negation normal form, all the negations are applied to leaves. A leaf is either labeled by a variable or by a constant. So the two leaves here are labeled by two variables, x and y. Now, here comes the interesting lemma. If phi is in negation normal form, then the De Morgan dual of phi is also in negation normal form. In other words, the De Morgan dual preserves negation normal form. If you input something which is in NNF, the output will also be in NNF. And I'll leave the proof of this lemma as an exercise. Okay. Our goal is to present an algorithm, which we denote by NNF, that transforms a Boolean formula into a logically equivalent formula, which is in negation normal form. So the input, phi, to the algorithm NNF is a Boolean formula that uses the logical connectives not, or, and. The base case says if phi is one of these 6 Boolean formulas, namely if the parse tree of phi has at most 2 nodes, then you return phi itself. Okay, so NNF of phi is 0, NNF of 0 is 0, NNF of 1 is 1, NNF of not xi is not xi, NNF of not 1 is not 1. It could be 0, but this is not an important case. For simplicity, we just return phi. Now let's focus on the reduction rules that apply if phi has a parse tree that contains more than 2 nodes. In this case, as before, phi is one of 3 forms. It is the negation of a subformula, an and of 2 subformulas, or an or of 2 subformulas. What do we do in each of these cases? Let's start with the 2 last cases, case 2 and case 3. If phi is the and of 2 subformulas, then you apply NNF recursively to the 2 subformulas, and you copy the and. You don't turn the and into an or, you keep the and. Same thing if phi is the or of 2 phi's, phi 1 is phi 2, you return the application of the algorithm recursively to phi 1, application of the algorithm recursively to phi 2, and you put an or in between. So these 2 cases are kind of simple, right? Because I did not encounter a negation, so I don't have to do anything, and I just applied the algorithm recursively to the subformulas. But what happens if I encounter a negation? And this negation is not applied to a leaf, because these are the cases in which the negation is applied to a leaf. So here, phi 1 is not a leaf. So what do I do in this case? Well, first I turn phi 1 into negation normal form, right? This is something I know how to do by the induction hypothesis. Now I apply De Morgan dual to the NNF of phi 1. We have a lemma that tells us that if NNF of phi 1 is in negation normal form, then so is the De Morgan dual of it. So we know that what we get here is indeed in negation normal form. But what is it logically equivalent to? Well, the NNF of phi 1 is logically equivalent to phi 1. This is what we would like. And dm of phi 1 is logically equivalent to the negation of phi 1, which is exactly phi. So this is why we do this strange application of De Morgan dual over here. The theorem says that if phi is a Boolean formula that uses the connectives not, or, and, then NNF of phi is a logically equivalent formula that is in negation normal form. Okay? So, there are actually 3 things that we claim about NNF of phi. The first thing it is a Boolean formula. The second thing, it is equivalent, logically equivalent to phi. And the third thing we claim, it is it is in negation normal form. 3 claims. Okay? So I'll leave this part as an exercise, and I'll focus on the 2 other parts. I want to prove that NNF of phi is logically equivalent to phi, and that it is in negation normal form. Okay, again, I want to emphasize that in the definition of negation normal form, what one could disallow not of 0 and not of 1, because you could always replace a not of 0 with a 1 and a not of 1 with a 0. But for simplicity, we do allow not of 0 and not of 1, and do not get confused by this somewhat not interesting point. Okay, so we want to prove that NNF of phi is logically equivalent to phi, and that it is indeed in negation normal form. The proof, as all the proofs we have in this part, are by complete induction on the size of the parse tree of phi, which we denote by n. Okay, I'm not going to give you the full details of the proof. You're supposed to fill them in by yourself. So complete the induction basis when n equals 1 or 2. State the induction hypothesis, and let's skip over to the induction step. So we know that phi has one of 3 forms: negation of phi 1, or of phi 1, phi 2, and of phi 1, phi 2. Now, I will leave the cases phi equals phi 1 and phi 2, phi equals phi 1 or phi 2 as exercises. So you need to fill in these details. And let me do the only case which I think is non-trivial, and that is the case in which phi equals the negation of phi 1. Okay, so we want to prove 2 things. We want to prove that in this case, NNF of phi is logically equivalent to phi, and that NNF of phi is indeed in negation normal form. Okay, so let's start with the first part of the proof. So NNF of phi, by definition, equals the De Morgan dual of the NNF of phi 1. Now, the induction hypothesis, when applied to phi 1, says that the NNF of phi 1 is logically equivalent to phi 1. So what we can do is we can substitute for NNF of phi 1, we can substitute phi 1. Okay, so this is the induction hypothesis plus substitution. Now, the De Morgan dual of phi 1, by what we have proved about De Morgan duality, is logically equivalent to the negation of phi 1. The negation of phi 1 is exactly equal to phi. So we get here equality to phi. Notice that this is equality, and this is equality, and here in the bottom. But these 2 are logical equivalences. Okay? So we get that phi is logically equivalent to the NNF of phi as required. Now we're left with the second part of the proof. We want to prove that NNF of phi is indeed in negation normal form. The proof proceeds as follows. Phi equals the negation of phi 1. NNF of phi is the De Morgan dual of NNF of phi 1. Now, NNF of phi 1 is in negation normal form by the induction hypothesis. And when you take a formula which is in negation normal form and compute the De Morgan dual of it, you get a formula which is also in NNF, because De Morgan dual preserves NNF. And that completes this part. Thank you.